This was one equation. We used conservation of linear momentum, and we tried to use some of our ideas about flow. Somebody may say, oh, wait, you really didn't talk about pressures acting on this contour volume. You have certain pressure field around it. But again, you can easily see that pressure almost all around this area is nothing other than atmospheric. So when you take atmospheric pressure, the horizontal components may not be atmospheric, but they don't give me any component of momentum in the z direction. The only pressures that are giving me components in the z are atmospheric in the bottom and the top, and the atmospheric pressure can be taken out of the system altogether, because when you take a scalar away from a pressure field and integrate the entire force of that pressure field around the closed object based on Gauss theorem, that would be zero contribution, so we can take atmospheric out. But the point that is very important, how I notice that pressure here, P at 2 is equal to P atmospheric, is a concept that we just talked about it in our review. Whenever the streamlines are flat and there is no curvature, the radius of curvature is going to infinity. So if I take a point here and move normal to streamlines like this, I'm not going to change the pressure at all. So if outside this jet pressure is atmospheric, inside this jet at any point pressure will be atmospheric too. So this idea that pressure everywhere here is atmospheric is the use of Euler equation normal to streamlines. Again, you can see the subtle use of certain concepts that we have learned in module 1 that helps you to really simplify this problem. Now that we have used conservation of linear momentum and helped from something like Euler normal to streamlines to talk about pressures, for example, in a cross-section, let's see whether we can use anything else to talk a little bit about connecting pressures between different points of this problem. Somebody may be tempted to say that, oh, I can use something like Bernoulli and then connect the pressure from here all the way to here. But we need to be careful. It's true that a streamline passes from this point to the other point, but this streamline goes through a blade that is getting or giving or getting some work and energy to the fluid elements as they pass through it. So we always need to be careful and think about it very carefully, that Bernoulli is conservation of energy. But if the system goes through a shaft or goes through a blade and gets some external energy taken or given to it, we cannot really use Bernoulli equation anymore. But any position before the blade and after the blade feels nothing other than an inviscid flow that is going through no exchange of energy with outside world. So I can certainly use Bernoulli between point 0 and point right before 1, which I call 1 negative, or between point 1 plus and point 2. I can certainly use Bernoulli between these two pairs of points, and let's do that together. So if I use, for example, Bernoulli, and I'm going to use it here, so Bernoulli between 0 and 1 minus, so this point and this point. At 0, velocity is 0. At 1 minus, I have a velocity which is u1. So connecting these together, I would get an expression which goes as P at position 1 minus is equal to P atmospheric minus half of rho u1 squared. In other words, pressure is atmospheric here. I accelerated fluid elements to a velocity u1, so pressure will drop, and will drop by an amount which is half of rho u1 squared. Similarly, between point 1 plus and 2, I can write down Bernoulli again. So again, another Bernoulli equation. And this time between points 1 plus and 2. And if I do that, I will get that P1 plus is equal to P atmospheric plus half of rho u2 squared. That's the Bernoulli constant in station 2 minus half of rho u1 squared. So I have one expression that describes pressure based on Bernoulli at position 1 plus, and I have another expression that describes pressure at point 1 minus. And now I can think of what really does these two pressures do for me. One is pressure right beneath the blade, the other is pressure right above the blade. It looks as if P1 plus is higher than P1 minus. And there are difference indeed. So if I combine star and double star, I can easily see that P1 plus is larger than P1 minus, and their difference is half of rho U2 squared. And the higher pressure beneath a blade compared to the lower pressure on the top, the difference between this pressure multiplied to the area of the blade, that's what gives the thrust force. So the thrust force can be also calculated using Bernoulli. And that would give me the thrust force is P1 plus minus P1 negative, the entire thing in the brackets multiplied to the area of the blade. And that would be equal to half of rho U2 squared multiplied to area of the blade. And this is what I call equation 2. Now clearly, equation 2 and equation 1 should give me the same thing because they are both giving me two different descriptions for the thrust force. So if indeed I combine equation 2 and equation 1, I will conclude that the CA, the contraction coefficient that I have for the area of the jet flow that comes finally away from the helicopter in the down in the position below the helicopter, should be equal to half of A, which is the cross-sectional area of the blade, and that tells me that this contraction constant is 1/2 or half. But more importantly, I have right now a nice expression for the thrust force of this helicopter, described as equation 2, or if you like, equivalent of that equation 1. They are both valid and you can use them with this notion that C, the constant, is 1/2. And what these two equations are telling me is the fact that if I have a blade with a certain area, and if it has to support its weight, I better manage to have a rotor strong enough to give me a velocity U2 large enough that will support its weight. So I really didn't solve anything in terms of the very complex dynamics of vortices and things related to the blade. I just took a step away, looked at the big picture, the big model of this geometry and this flow and this phenomena, and used my understanding of conservation laws for both mass and momentum, and something related to energy which is captured by Bernoulli equation in regions that is valid to use, either before or after the blade, not through the blade. And I found something interesting and useful that I can use in my engineering calculations. In the exam for module 1, you will probably see or deal with problems like this. Things that are apparently complex, but if you take a step back and take a nice simple control volume around it, you can easily solve it and get accurate engineering solutions for your problem. One thing that is very important here is the fact that velocity remains continuous as it passes through this blade. But pressure, as you have seen, feels quite a bit of increase. This increase in pressure, if you like to think about it physically, is happening because of the fact that you are doing some work and energy. So as the flow passes through this blade at a constant velocity, that work and energy that you are doing on fluid elements will lead to some increase in the pressure. With this, I hope that you will enjoy and benefit from all the review videos that we captured in this session. And I hope that you guys will also watch one final set of slides that we will show in the next video, which will tell you a little bit about this example and connect it to the picture of the module that we have posted on the online page. And also will give you a taste and a kind of a short intro and invitation for what will be covered in module 2. So I encourage you to watch the next video, and thank you for following this problem.